Okay, so this topic is about gyroscope. As you can see in this figure, this is how the gyroscope look like. So if you consider this toy gyroscope that's supported at one end, so this is the pivot. If we hold it with the flywheel axis horizontal, as you can see in this case here. So if you this is consists of this axis here, and then you have the axis of uh, this flywheel, and the flywheel is attached to this axis here. So if we hold it with the flywheel axis horizontal and let it go, the free end of the axis simply drops, owing to gravity. And if the flywheel is not spinning, so if the flywheel is not spinning about its own axis, so it will just drop. But one interesting motion of the gyroscope is a steady circular motion of the axis in a horizontal plane, uh, combined with the spin motion of the flywheel about the axis. And this surprising and non-intuitive motion of the axis is called precession. And this we will explain how the gyroscope move uh, about about this point here. So if the this wheel is spinning, wheel of the gyroscope is spinning, and we put this one end on this support here. So the flywheel and its axis together will rotate about this axis here. So this omega here is what we call is the precession. Okay, so to study this strange phenomena of the precession, we must remember that the angular velocity, angular momentum, and torque are all vectors quantities. Okay, so let's first assume the flywheel is not spinning, as you can see in this case. So uh, we take the origin O at the pivot, which is this point here, and assume that the flywheel is symmetrical. So a symmetrical flywheel with a mass m. So the mass of the flywheel is m, and the moment of inertia of the flywheel is I, about the axis, about the flywheel axis. So which is this is the flywheel axis, the x-axis here, and the flywheel axis is initially along the x-axis. Now the only external force on the gyroscope are the normal force N, so which is this force here. So this force here, uh, acting at pivot, assumed to be frictionless, and the weight W of the flywheel, which is this force here, that acts its center of mass, a distance r from the pivot. So the distance between the flywheel and the pivot point is r here, and this W is the weight of the flywheel. And initially the flywheel is not spinning about its own axis. So the normal force has zero torque, as we know that this normal force, which is the force that pivot is acting on the flywheel axis, because it's passing through this axis here. So its moment arm is zero, and it will produce no torque. Uh, and the only torque that you can have in this case is produced by the weight. Uh, so the weight will produce only torque here, and as you can see by the vector cross product, if you just uh, keep your finger in the direction of r, and rotate it toward W, so then the thumb will point in the direction of tau here. So r into W is equal to tau, so which is this thing here. And the direction of this tau is, you can calculate by right hand rule. So if you uh, keep your fingers in the direction of r and rotate it toward W, so then the tau, which is what we call is the torque, is going to be in this direction here. Now initially there is no rotation, because the flywheel is not spinning in this case, and the initial angular momentum Li is zero. Now, as you know that the if you look at this figure from the top, so this is how it will look like. So this is the pivot point, and this is the axis of the flywheel. Now the flywheel is not spinning about its own axis, and therefore the initial angular momentum is zero, uh, because we know that angular momentum Li is equal to uh, mass times velocity. So in angular case, it become I omega. So this means that the omega is zero for the flywheel. So if it is not spinning, so this means that omega is zero. So this means that if it is not spinning, so this means that the initial momentum of this flywheel will be zero. So Li is zero. Now the change dl in the angular momentum in short time interval dt in y direction, which is this direction here, uh, or you can see in this case here, because the flywheel is, if you let it drop, so it will just move in this direction here. Uh, so we know that as we know that this tau is equal to dl by dt. So in this case, what you can write is dl is equal to tau dt. So because here we have tau, so due to this tau, which is torque, we will get some angular some change in angular momentum here, which is you can represent by dl. So dl means that it will be a slight increment of the angular momentum, and then you can calculate it by using this tau dt. And because the initial angular momentum is zero, so this angular momentum after each time dt, it will just add up, and this means that the final angular momentum in this case will be just Li, which is zero, and plus dl. Uh, so this means that this and then in the next dt, it will be dl plus dl, and then in the third case, it will become dl plus dl plus dl. So at each time interval, there will be an addition of dl, and we can see that all these dl will act in a same direction. So there will increase in this angular momentum here. So this is how these will add up together, and we know that this angular momentum is a vector, and because all these are acting in the same direction, so therefore um, it will be just some of these small intervals. Now, as each additional time interval dt elapses, the angular momentum changes by additional increment dl, as you can see here in the y direction, and the direction of this is obviously in the y direction, which is in the direction of the tau, because the direction of the torque is constant here. Now the steadily increasing horizontal angular momentum means that the gyroscope rotate downward faster and faster around the y-axis until it hits either the stand or the table on which it sits. Okay, so now let's see what will happen if the flywheel is spinning. Now in the previous case, we assumed that the flywheel was not spinning, but now we are assuming that the flywheel is spinning with some angular velocity here, which is omega. And if the flywheel is spinning, so because we know that Li is equal to I omega. So this means that that Li is now not zero, because we have uh, the flywheel should have some I, which is moment of inertia, and if it rotate about its axis, so it will have some angular velocity. This means that the angular momentum is not zero here, but there will be some angular momentum, which you can represent by this Li. So initial angular momentum of the flywheel here. And so if the flywheel is spinning about its center, and obviously it's spinning in this direction here. So if you curl your finger in the direction of rotation, so then your thumb will point in the direction of the omega, and the direction of omega is again the direction of the angular momentum here. So this means that the angular momentum direction is also in the direction of omega here. Okay, now since the flywheel rotate around its symmetry axis, Li lies along this axis. So Li is also about the x-axis. But each change in angular momentum dl is perpendicular to the flywheel axis because the torque is perpendicular to that axis. Okay, now what happened that the initially, as you can see in this case here, that the initial angular momentum was in this direction here, and now we know that this dl, which is equal to tau dt. So this dl, which is the change in angular momentum due to this tau, will be in this direction here, in the y direction, as you can see in this figure here. So this, you will see a little bit a little increment of this dl here. And now if you want to calculate the final angular momentum here, so we will just using the head to tail rule, because these are vectors, and this will be the final angular momentum here. Now in this case, the interesting point is that uh, that the Li, the Li and Lf, so the magnitude of Li and Lf, if you consider the magnitude of Li and Lf is exactly the same. The only difference is this dl. The dl is just changing the direction of Li. So the direction of Li is changing from this point to this one. So if you call this maybe LF1, and then it will become LF2, and then this will become LF3. So this dl is changing the direction of this Li. Okay, so now this causes the direction of Li to change, but not its magnitude. And the change dl are always in the horizontal xy plane. So the angular momentum vector and the flywheel axis with which it moves are always horizontal. So this means that the whole due to this change in momentum, the whole thing will rotate about this axis here. So that is, the axis doesn't fall, it precesses. So this means that Li chases tau. So this means that this Li is chasing this tau, which is the torque vector. So the whole flywheel is with its axis is rotating about this pivot point in this direction here, or in this xy plane here. So the whole thing will rotate like this. Now at the instance shown, the gyroscope has angular momentum L. So now if you assume that one case here, that you have this that if the uh, the angular momentum is L, the initial angular momentum, and then a short time interval dt later, the angular momentum is L plus dl. So then the new angular momentum will become L and plus dl, and this is a vector addition here, and you will just add L plus dl here. So this will become the final angular momentum here. So Lf is the final angular momentum, and this was our initial angular momentum, which was L here. And there is this angle between the L and L plus dl, which is d phi here. You can show this by d phi. And this infinitesimal change in angular momentum is dl, which you can write is L d phi, because we know that S is equal to r theta. So if you want to calculate here, so this is your S and this is your R. and this d phi is your d theta. So S will become equal to r theta, or in this case dl, which is S, will become equal to l d theta, which is r theta. And obviously this dl is perpendicular to l here. So in this case, you can say that this dl is equal to l d pi. Uh, okay, so in this case, if you divide both side by dt, so in this case, what you see here, uh, that you have this equation that dl by dt is equal to l d phi by dt here. So the rate at which, so now this is the rate at which this angle is changing. So now obviously we know that omega is equal to d theta by dt. You already know that angular velocity is equal to d theta by dt. Now, so this means that the rate of change of angle is velocity, angular velocity. So the rate at which the axis move, which is d pi by dt, which is this thing here, is called the precession angular speed, because this the rate at which this angle is changing is, this means that the whole thing is moving around the axis of this gyroscope, is called the precession angular speed, and denoting this by this capital omega here. So if we represent this d pi by dt by this thing here, so if we just show this by this symbol here, which is a capital omega here. And again, we know that dl by dt is, according to the Newton's second law, is tau, which is the torque. So this means that we can simplify this equation, that tau is equal to L, and you have this thing here. So tau is equal to L times this capital omega, and in this case we can also simplify this L. So L is the initial angular momentum, which is we know that it is just I omega, and this omega here. So we have this equation now. So this L is, so this is our L here. This is the L here. So we just putting here the value of the L. So now in this case, if you want to calculate the precession angular velocity here, so which will become T divided by IW. And in this case, we know that this torque can be calculated by the weight of the flywheel multiplied with the distance from the pivot point. So we know that it is just R times weight and divided by I omega. So the precession angular velocity, so this means that the whole, if you consider this is our X and Y, this means that the whole thing will rotate here. Okay, so thus the precession angular speed, which is this here, is inversely proportional to the angular speed of the up spin about the axis, which is omega. So this precession angular velocity is inversely proportional to the angular velocity of this flywheel about its own axis. Okay, so now we want to solve this one numerical example here, and this example is on the gyroscope, and it is taken from your tutorial sheet. Okay, so this figure shows a top view of a spinning cylindrical gyroscope wheel. The pivot is at O, so this is our pivot point, and the mass of the axle is negligible, so you can neglect the mass of this axle here. Okay, so and again you are given some dimensions here. So the distance from here to here is 2, and the radius of the flywheel is 3 here. So as seen from the above, the okay, is the precession clockwise or counterclockwise? So the first thing that you need to calculate is direction of precession you need to calculate. And B, if the gyroscope take 4 seconds for one revolution of precession. So this means that in part B, what you are given, that you are given that this precession angular velocity. So if the gyroscope take 4 seconds for one revolution of precession, so one revolution means 2 pi in 4 seconds. So this is the this will be the velocity. So distance divided by the time. The angular distance divided by the time will become the angular velocity here. So 2 pi divided by 4 is the uh, is the precession angular velocity, and then it will become 1.57 radian per second. Okay, and what is the angular speed of the flywheel? So what you need to calculate is omega, which is this omega here. You need to calculate this omega here. Okay, so first you need to calculate the direction of this uh, precession angular velocity here. So in part A, we will have to draw the so if you consider this is our flywheel. Okay, so the flywheel is rotating in this direction here, omega. So this is the direction of the omega here. Now, if you want to calculate the direction of the omega according to the right hand rule, so you will just curl your finger in the direction of omega, and the thumb will point the direction of omega here. So this means that the direction of omega is this direction, which is omega. And we know that the direction of L is also in the direction of omega. So this means that L will be in this direction here. So this is our L. Okay, and now we need to calculate DL, and we need to find out the direction of DL. So now if you just let this flywheel drop, so what will happen that and you can see that R is in this direction. So this is our R, and the weight of the flywheel will act in the downward direction. So if you take your right hand and just put your finger in the direction of R and move toward W, then your finger will point in the direction of the direction of R, the direction of tau. So this means that tau is in this direction. So tau is in this direction here. So as you can see here. So if you just put your finger in the direction of R, which is this R is the distance from the pivot point, which is O, to the mass center of this gyroscope or the flywheel, and the and in this case the weight is obviously in the uh, inside the plane of this paper. So if you curl your finger, so then the tau is going to be in this direction, because tau is equal to R cross W, which is a cross product of R and W. So this is how you will calculate the direction of R tau, which is the cross product of two vectors. One is R vector, one is W vector. So this means that tau is obviously in this direction here, and W was in this direction, and L is also in this direction here. Okay, so now if T is in this direction, so this means that because we know that dl is tau dt, because tau is dl by dt according to the Newton's second law. So dl become equal to tau dt. So this means that the change in momentum will equal to tau dt, and this will be in the direction of this tau. and tau is in this direction. So this means that the dl will be in this case in this direction here. So this is our dl, and now we need to calculate the final. So this is our l plus dl. So this means that this is our d pi here. So this means that the flywheel with its axis will follow in this in this direction here. So this means that the whole thing here will just rotate in this direction here. So this is our precession angular velocity here, so which will move in this direction of the dl. So this means that this whole thing will just rotate this way here. So this is our part A. So direction of uh, this precession angular velocity, and from here we can see that this precession angular velocity is clockwise. This is the part A. Now in the part B, you are given this capital omega, and you need to calculate the omega. So you are given the precession angular velocity, and you need to find out the angular velocity of the flywheel. So we know uh, from the theory that we just derive this equation, that tau is equal to I omega into this one, the precession angular velocity. So then we also know that this tau is r times w, and is equal to I omega this. And now in this case we need to calculate this omega here. So what you calculate is rw divided by I and this capital omega here. Okay, so now we know that this w is just mg, and I of the we know that the moment of inertia of this cylinder, you know that the moment of inertia is you can see this in your formula sheet, that the I of the cylinder is I mr square. So r is the radius of the cylinder, m is its mass, and half. So this is how you calculate the this I here. So you will also just put this value here. So half m r square. So this r, capital R, is the radius of the flywheel, and this small r is the distance between this O and the center of mass of the flywheel. So you should differentiate between this small r and capital R here, and obviously we will have this term here. Okay, so now in this case, because we have m here and here, so we can cancel m. Uh, so if you just simplify this equation, it will become 2 rg divided by r square, this one. So w become equal to 2. Yeah, from the diagram you can see that r is just this distance here, so which is 2 centimeter. So 2 into 10 power minus 2 meter, changes to meter, and g is 9.81, and r is just the radius of the gyroscope, which is 3 in this case, or 3 centimeters. You need to change this to meter, and you are also given this this value here, so which is this value here, 1.57. So from here then you can calculate the value of the omega, which become 280 radian per second, and which you can also convert to revolution per minute if you are interested in. So it will become 2600 revolution per minute.